Today we're going to take a look at the effect of atomic structure on the properties of an element. So we're going to see exactly how this works. So first we should talk about the different forms of energy. So energy is the ability to do work, and energy can come in different forms, such as light, also referred to as electromagnetic energy, nuclear energy found in the atoms of substances, mechanical energy, chemical energy, such as the chemical energy found in the bonds of substances, electrical energy, and thermal or heat energy. Okay, so in terms of electromagnetic radiation, this is a form of energy that has wave-like behaviors. Okay, so there are different forms of electromagnetic radiation as indicated on this diagram here, from radio waves that transmit signals that people use in the radio industry, to microwaves, the same types of radiation found in your microwave oven, to infrared radiation given off by the sun. And then you have visible light, which is found within this range of the electromagnetic spectrum, to harmful ultraviolet or UV rays found also given off by the sun. And then you have even more dangerous forms of radiation, such as X-rays, the same X-rays used to take pictures internally, if you have a fracture or something of that sort, to the most probably harmful types of rays, gamma rays. Okay, so all of these are different forms of electromagnetic radiation, and the visible light spectrum falls within here. And we typically use the mnemonic Roy G. Biv to remember the order. So from your reds, your orange, your yellows, your greens, your blues, your indigos, and your violet. Okay, so as I mentioned, these are the different forms of electromagnetic radiation. So visible light, radio waves, microwaves, infrared, UV, X-rays, and gamma. Okay, so waves have particular characteristics. So we describe waves by the wavelength, which is the distance between equivalent points on a wave. And we use the units nanometers, which is 10 to the negative 9th meter. So 1 billionth of a meter. So it's very, very small here. So as indicated on the diagram here, the wavelength is the distance from one point of the wave to the other. And then the frequency is the number of waves that pass a given point. Okay, so it's describing essentially the speed of the wave. Okay, so we measure the speed of the wave by the frequency. We call the top of a wave the crest. We call the bottom of a wave the trough. And then the height from the crest to the center point here is referred to as the amplitude of the wave. Okay, and it's important to note that visible light consists of the following colors. So you have red light, which is approximately 650 nanometers, orange, which is about 590 nanometers, yellow, which is approximately 570 nanometers, green, which is about 510 nanometers, blue, which is about 475 nanometers, indigo, about 445, and violet, which is about 400. So it's important to note that out of all of the colors within visible light, red has the largest wavelength, but it's the least dangerous in a sense. It's the least dangerous. Whereas violet has the smallest wavelength within the visible light range, but it's actually more dangerous in terms of how much damage it can cause. Okay, so we say that light, it's an interesting substance because light behaves both as waves and it also behaves like a particle, like matter. So we describe light as photons. So, they're like, we describe this as the dual nature of light, because typically it's either one or the other. But it's quite interesting that light behaves as both a wave and as a particle. Okay, and then there's something else referred to as the atomic emission spectra. So the atomic emission spectrum of an element is the set of frequencies of the electromagnetic wave emitted by atoms of the element. So an element's atomic emission spectrum it's unique, and it can be used to identify what the element is. So this emission spectra is almost like a fingerprint. So much in the same way a fingerprint can identify a person, the atomic emission spectra can identify what the element is. So if you take a look at this diagram here, you see that there are several substances. There's an unknown substance. There's beryllium, there's copper, manganese, strontium, and titanium. And if you look at beryllium's atomic emission spectra, you see there's a purple line here, followed by a blue, followed by like a teal here and a green here. And then for copper, you see that there are these three emission spectra here, sort of like in the yellowish range. And then manganese, you have this purple, followed by this blue, followed by this other lighter blue and like a greenish yellow, and then so on and so forth. So these lines actually mean something. It's indicating what the substance actually is. So beryllium is only going to have this set of emission spectra. Copper is only going to have this set in this range here, and then so on and so forth. So if you take a look, you have this unknown here. So if you were to compare the unknown up here to one of the 5 down here, you can see that this set of lines up here is similar to strontium. So we can use the emission spectra to identify what a substance is because, as I previously mentioned, elements are going to have a characteristic emission spectra. Okay, and the way the atomic emission spectra works is that when an atom absorbs energy, the electrons move from the stable level, referred to as the ground state, and they move to an excited state, to a higher energy level or shell. Okay, and then the excited atoms return to their ground state by emitting light to release that energy. And then the lowest allowable energy state of an atom is called the ground state. And when an atom gains energy, it's said to be excited. So this is similar to a lab that hopefully we did before, where you took some substances and put them in a flame, and you saw the different colors of the flame, the flame test. So it's related to this idea that when an atom gets excited, the electrons are going to move to a higher energy level, and then they're going to come back down to their normal level or their ground state, and they're going to emit or give off energy in the form of light. Okay, so this diagram here is trying to demonstrate this idea. So you have this atom that's in the ground state, and then you have this electron here that's at this level. So if that electron gets excited from a photon or from light, that electron is going to jump from this ground state to a higher level. Okay, but it doesn't want to remain at that higher level. It's going to come back down to its normal level or ground state, and it's going to give off energy in the form of light, in the form of photons. So this is the theory or the principle behind why the flames change color when we put the substances in the flame. Okay, so this diagram here is trying to show like a variation of the flame test. So there are different substances here that were lit, and they all have different colors based on the arrangement of the electrons, and the colors give you an idea of how much energy is being released. So your reds are your lower energy or lower frequency wavelengths, and whereas your blues are higher frequency. Okay, and then this leads us to another model of atomic structure. So we saw that over the years there were different theories of atoms and how they were arranged. So another model is referred to as the wave mechanical model, and it describes the probability or the chance of finding an electron within a particular volume or space or area or region. The region where it's found is referred to as the atomic orbital, which is around the nucleus. And so the atomic orbital is the region or the space or the area around the nucleus where electrons are located. And sometimes some books refer to it as the electron cloud. Okay, so these diagrams here, it's a little complicated here, but all of these circles on the outer level represent the levels, the energy levels. And the wave mechanical model is saying that there's a chance of finding these electrons in these areas here, in this region here. And this leads us to the principle of electron configuration. So the arrangement of electrons in an atom is called the electron configuration. The first level can only hold a maximum of 2 electrons. The second level can hold a maximum of 8 electrons. The third level can hold a maximum of 18 electrons. Okay, and then we're going to refer to your periodic table for a little bit and draw some of these electrons, their electron configuration. Okay, and then this leads us to the idea of valence electrons. So valence electrons are electrons that are in the outermost level. And this is a very important concept here, because these valence electrons determine the chemical properties of the element, and they're the ones that are going to be involved in chemical bonding. So we use something called an electron dot structure or Lewis dot structure, which consists of the element symbol, which represents the nucleus, and the inner level electrons surrounded by dots representing all of the atom's valence electrons. Okay, so we're going to take a look at some examples, and this will be cleared up through some problems. Okay, so you're going to work on a couple of problems to really gain a better understanding of this, to practice some of these ideas. Thanks.